Well, it looks like the chair did a great job. We're exactly on schedule, and the next paper has 6 minutes.
You got 5 minutes.
We're actually 9 minutes behind schedule. So each of the papers, the first 5 are running about 17 minutes long, so we'll sort of slide the rest of the people too. And I'll stand up when the speakers have about 3 or 4 minutes left, so we can have some time for questions. The next paper is Acetonitrile Synthesis from carbon monoxide, hydrogen, and ammonia over supported iron catalyst. The authors are A.A. Hummel, M.D. Bandani, K.E. Hummel, and W.N. Delgass, and Nick Delgass from Purdue University will present the paper.
If I could have the first slide, please. This will now go back a little bit toward what we were talking about earlier, namely effects of support on the nature of reactions, effects of particle size on the nature of reactions, and talk about some iron catalysts for a synthesis type reaction. In this case, what we're doing is following a Monsanto patent, adding to the CO hydrogen mixture ammonia, and looking at the nitrogen-containing products, in this case acetonitrile. Temperature region is chosen so that we are in the region which thermodynamically will permit the nitrile formation. If you work at lower temperatures, you accentuate the amines. If you go to a little bit higher temperature than this, you accentuate HCN. If you go to much higher temperature than that, the ammonia decomposes too fast and you get relatively little reaction. So we're in a window thermodynamically where the acetonitrile is stable. We expect some acetonitrile and some HCN, and we push that window toward the HCN side to accelerate the kinetics to some extent. You notice that we are working in a slightly non-stoichiometric mixture, a CO4 mixture with respect to stoichiometry. The reaction is 0 order or negative order in CO, and we can prevent the side reactions by not pushing the CO too hard. And these are close to the conditions that are reported in the patent literature to be interesting ones for this particular reaction. The catalysts that are proposed for this reaction are molybdenum-based and iron-based generally. We've chosen the iron-based system because it affords us the Musbar effect as a way of characterizing the catalyst and trying to understand some of the things that are involved in the catalytic activity. The patent literature also suggests that you get a better catalyst if you pre-nitride the catalyst. And so we're interested to find out what is the effect of nitriding and what is the duration of that effect of nitriding. I want to tell you a relatively simple message this morning. We've looked at 3 different catalysts, and my main message this morning is to try to convince you that in order to make a stable catalyst, to have this reaction run, you want a material which has the smallest iron particle size. So what we're going to see is that we have what appears to be a particle size effect, but it's a particle size effect not on the reaction that we're interested in, but on the poisoning reaction, which is the coke formation in this particular system. We're going to look at iron, unsupported iron, iron on silica, and iron on carbon. Let's look at the iron on silica system first, and let me use the Musbar effect to describe to you the differences between 3 of the catalysts that we have made. The reference spectrum on the bottom is the magnetically split iron 0 spectrum that you get for bulk iron powder or iron foils. And what you see in these 3 catalysts, and in this case catalyst A and catalyst C, are essentially identical. And what's interesting about these materials, which are 4% iron on silica reduced at 673 Kelvin for about 12 hours in hydrogen, is that the states in this envelope are 2 different doublets for iron 2+. All the iron 3+ has been reduced, but no iron 0 has been made, neither superparamagnetic iron in the center, nor any magnetically split iron. So these 2 catalysts have essentially iron 2+ as their main phase after reduction, and this catalyst B is a mixture of iron 2+ and some 0-valent iron metal with a slightly smaller hyperfine field than the bulk material, particle sizes of the order of 70 to 100 angstroms of iron metal. The catalytic behavior of these materials is remarkably different. If we look now at the effect of time on stream for the production of acetonitrile over these catalysts, and these are if you normalize the rates to the surface area of of Fe2 plus titratable by NO chemisorption. Turnover numbers are of the order of 10 to the minus 3. We're looking at low conversions here, about 1%. The product distribution is HCN is greater than methyl cyanide is greater than methane, and those are the main products of interest. The irreducible catalyst, the one that had only iron 2 plus, has very low activity in the beginning and builds slowly to a stable activity. The catalyst that had some iron 0 in it rises to a high activity, but then has a poor stability. It decays over time continuously. The characteristic shown here is also repeated in many other situations. If you pre-nitride the catalyst by heating it in ammonia at 673 for several hours, you can convert the material to Fe2N, and starting with the Fe2N precursor, you get a more active catalyst initially, but this catalyst shows an even more severe decay activity than the pre-reduced catalyst. So 3-4% iron on silica catalysts have significantly different behavior, but the characteristic that seems to be important is whether or not they have iron 0 in them to start with. If we now look to this description and say, well, let's go to the limit and look at unsupported iron 0 and see what the effect of the reaction is on that, what we find is the following behavior in this upper slide. Over a short time period now, over the first hour, what we see is very little acetonitrile. Sometimes a burst of acetonitrile right at the beginning, but the main reaction that goes on over unsupported iron is a combination of the Boudouard reaction, which is depositing carbon to make the carbide and coke on the surface, and subsequent water gas shift, or reverse of the water gas shift, to produce water and CO2. So the unsupported iron catalyst is very unstable. Its initial rate for acetonitrile production is comparable to the very early behavior of the supported catalyst, but the iron 0 is very quickly poisoned by carbon deposition. The results of the irreducible catalyst, again, is to build a concentration of acetonitrile production, and there are some interesting early transients here, but I want to focus on just the steady state or progress toward the steady state in this particular case. If we now look at a characterization of the nature of these materials, and remember that the nitrided catalyst, even the nitrided catalyst which has essentially no reducible iron to start with, showed the behavior which is a rise and decay which we are trying to attribute to iron 0. We need to use the Musbar effect now to follow why that's happening and see whether we can in fact attribute that pre-nitriding condition to a change in particle size and the eventual production of a large iron particle phase. First, let's look at the reduced catalyst. This is that B catalyst, which has some iron 0 and some 2+. If we run for 15 minutes of reaction in situ in the Musbar cell, we see no iron 0 left. If you analyze this spectrum, you will find epsilon prime iron carbide in about the same amount as there was original iron 0. So the effect of the reaction is to turn the iron 0 into iron carbide, and we think that's the behavior that we're looking at for the high activity. The iron 0 is converted to the carbide is initially active, but then the carbide decays because it cokes because the particles are too large. The effect is even more pronounced on the nitrided catalyst, and interestingly, if we take this we nitride the catalyst, which before in hydrogen was not reducible, and treat it with ammonia, we see that all of the iron can be converted, essentially all of the iron can be converted to the nitride, so that the ammonia can break the iron silica interaction and form nitride particles where the hydrogen cannot reduce to iron metal. And this catalyst, once we start 15 minutes worth of reaction, is converted almost entirely to the epsilon prime iron carbide again. This tells you that the nitride itself is not the stable component for reaction. The nitride is rapidly lost and converted into the carbide. These carbide particles are fairly large, and they exhibit the large particle self-poisoning phenomenon that I've mentioned before. If we re-reduce this sample, we see that there's a little bit more iron formed, but the iron particles are still in the 100 angstrom region, If we re-reduce this nitrided sample, we see essentially all the iron goes to the magnetic phase, and this is larger particles where there's no change, no diminution of the hyperfine field in the iron. So the conclusions that we come to are that the larger the particles of iron, the more likely it is that you will make this carbide phase, but you will have a self-poisoning effect due to the presence of the large particles and the ability to form coke. If we press that, what we should say then is we should look for the smallest possible iron particles that we can make and see if we can get a more stable catalyst. And to do that, we turn to the iron-on-carbon system, which has been reported by several people in respect to the CO hydrogen reaction by Jung and Van Nuys. And if we follow their prescription for taking the sulfur out of this 1,200 square meter per gram high surface area carbon, deposit iron on it, and then look at the stability for acetonitrile of the reduced and nitrided catalyst, we see there is a little bit of initial drop in activity of the pre-nitrided catalyst, and we don't have the first data point for the pre-reduced catalyst. But the strikingly different behavior here is that this catalyst is very stable over time for the acetonitrile production, and we think that's because these particles are very small. When you look at the Musbar effect of these particles, you see that they are super paramagnetic, just a little bit of magnetic material, combination of hydrogen desorption, of Musbar analysis, and TEM analysis shows that these particles are in the 30 angstrom diameter region, and these particles are in fact quite stable. So if I summarize the results of what I would like to tell you, first I would repeat that the iron zero unsupported material has an intrinsic possibility of activity, but it dies immediately because of coke formation. The best stability for this catalyst is found in the smallest particles of iron, and in this case, those particles, the most stable ones we can make are the ones on the carbon. And we would also say that the pre-reduced iron 2+ only catalyst, which grows very slowly to a stable activity, we would ascribe to the growth of very small crystallites of iron zero in the reaction medium, and those are small enough to hold this stable activity. Interestingly, if you take that kind of catalyst and nitride it, then you essentially break that strong iron-silica support interaction and form nitride particles, which then can sinter. But we find that the activity, or the nitriding, has this phase and particle size effect, but the nitride itself is not the stable active phase for this particular catalyst. We are in the process of some transient isotope tracing reactions or studies to look at the mechanism of this reaction. Nitrogen-15 tracer experiments would confirm the idea that the active catalyst has no large pools of nitrogen in it, because we find that the nitrogen pool, active nitrogen pool on the surface, is quite small. The carbon pool is rather complex, and we're still in the process of sorting that out. Thank you very much.
Questions, please? Would you like to ask a question of the audience? No? Okay, I think maybe taking some time will make it. Whoops, stop.